Hi everyone, I'm Yuan from Shanghai University. It's my pleasure to share this interesting topic about an experimental investigation on morphological evolution and the coupling between shoreface nourishment and the natural profile under large wave conditions at the International Conference on Coastal Engineering 2020. My talk includes introduction, experimental setup, main findings, and finally concluding remarks. Due to global climate change and population growth, the natural region is a particular hotspot that has become increasingly tropical and politically sensitive worldwide. In the context of widespread coastal crises such as beach erosion, overtopping, and inundation, specifically, half of China's any beaches are under the risk of severe erosion. And these three short videos about overtopping were recorded during Typhoon Yakima. Yeah. As a solution, surface measurement is conducted by filling sands of similar properties to form submerged artificial sandbar, which has been proved effectively in reducing coast erosion. When the artificial sandbar is implemented on the surface, there would be a strong connection between it with natural profiles. For instance, artificial sandbar has two functions in sense of pitch protection, that is, lee and feeder effect, while the natural background profile affects artificial sandbar evolution by its elusive or migrative type and sand exchanging. It is well recognized that as natural bars will migrate or evolve according to the wave climate and the sand's properties. Its hydrodynamic environment and the sediment transport patterns are very clear. And due to the variance between the natural bar and the artificial bar, the consensus of natural bar cannot be applied to submerged artificial bar directly. Researches have also been carried out on the submerged artificial bar in the field or in the lab to investigate their possibly lee and feeder effect. However, the submerged artificial bar itself, morphological evolution, and their interactions with the natural profile are still recovered. Hence, the key research questions of this study uh, is the morphological evolution of artificial sandbars under large wave conditioning, and the morphological coupling between artificial sandbars and natural profiles. To deal with it, a series of tests have been conducted in a wave flume. The flume is 50 meters long, half meter wide, and 1 meter high, and is covered with a water depth of 0.6 meters in the horizontal section. The flume is equipped with a paddle type wave maker, which is able to generate wave heights up to 0.3 meters. Wave are generated in Johnson wave spectrum with peak enhancement factor of 3.3. The first 30 meters of flume length is used to allow for wave adjustment. Then beach of 16 meters long and 1 to 20 slope consisting of 1,000 natural sand with D50 of 0.23 millimeter is constructed with its toe at a water depth of 0.6 meters relative to sea level. Wave gauges are used to measure wave surface elevation with a sampling frequency of 50 Hz. The bottom elevation is measured with a tremble scale X configuration scale with area less than 1 millimeter. Before construction of artificial sandbars, two types of background profile, as the berm named profile A and the barrier named profile E, have been firstly generated from original 1 to 20 sloping profile under accretive and erosive wave conditions. So omega for the two background profiles are 0.86 and 3.3 respectively. Berm profile tended to be equilibrium after 14 hours wave action. The berm height is 11 centimeters and its foreshore slope is very steep. The outer profile is double buried with outer bar locating from 5 to 7 meters and inner bar located at 6 meters. After that, as shown in the red picture. say artificial sandbar has been implemented on the shoreface. For better clarify the design of artificial sandbar, it is necessary to define sandbar morphology parameters. In the left figure, HC means water depth over bar crest, and H bar means bar height, and S on and S off represent shoreward and seaward bar slope, respectively. The shape of artificial sandbar is designed to be triangular, since a more concentrated nourishment better protects the pre-nourished profile. Both slopes of artificial sandbar are designed to be about 4 times larger than natural profile to make a distinction. On background barrier profile, artificial sandbar is placed on the shorewater or seawater side of the natural outbar. Their volume are in the same magnitude. On background berm profile, artificial sandbar is placed near the berm with HC ranging from 0.07 to 0.12 meters, and also ranging from 0.19 to 0.27. The wave condition generated in the background bar profile is chosen to represent the large wave condition for each case. Time intervals for profile measuring are not fixed, but adjust according to the time-varying profile evolution rate. Here, main findings are provided. Firstly, better profile evolution is analyzed. Artificial sandbar migrates onshore with their shapes dissipating gradually. To be specific, spar height decreased and both sides of slopes became mined. Moreover, significant overwash deposits are all observed on the backshore of the berm at the end of each case, where the fusion bar morphology has been dissipated sufficiently. So overall sediment transport is onshore directed. Berms are well protected at the beginning, while major erosion occurs only when shapes of artificial sandbar are significantly dissipated, implying a morphological hysteresis existing. Shoreline retreat and decrease in front slope of the berm are observed at the end of each case. Hence, the effect of sandbar is dynamic and affected by their morphological stability. Shoreward placement of artificial sandbar provides more protection for the beach in our experimental settings. The bar height shows a rapid decrease in the beginning and then tend to be equilibrium. As a half-life period at half, defined as the time required for the bar height to be decreased by half, is a key parameter to reflect the bar stability. The half-life period of artificial sandbar is influenced by S-off and the ratio between the bar crest height to bar height, which are both time-varying. In terms of berm response, the berm slope, berm front slope is the average of the flat slope above the stilt level. Then the berm rollover tan theta is defined as the slope between the positive direction of x-axis and the line connecting berm height position to initial shoreline location. To involve sediment transport from the front of the berm to the top and the back of the berm for overtopping and overwash processes. However, an obvious increasing trend occurs before decreasing in the period from 0 to 0.6 in the berm front slope. That to say is tend to be evolving, indicating that there is a morphological hysteresis of berm response to erosive wave impacts. As a berm rollover tan theta acts as an indicator of berm overall behavior, and in the beginning, berm rose landward in high rate in each case. After the first however, the evolution of tan theta tends to be equilibrium of approximately 0.7. The higher landward roll rate indicates the mismatching between initial accretive profile and the prevailing erosive wave condition. On the given wave condition for sufficient time, the berm tends to be equilibrium. As mentioned above, there exists a strong morphological coupling between bar decay and berm erosion. In each case, berm changes to adapt to the wave condition. Here, in Parachrom parameter B, incorporating these three factors, is defined to reflect berm behavior, in which the first term on the right-hand side represents berm slope changes, and the second term means berm movement in coastal direction. The last term is berm elevation changes in the vertical direction. B large is 1 represents berm acceleration compared with the berm state at the inflation and the timing submerged artificial sandbar implementation and vice versa. Meanwhile, another empirical parameter is defined to describe the degree of the bar morphology, while the first term in the numerator is a surface similarity parameter based on seaward slope of the artificial sandbar. This term in a large magnitude indicates a high possibility of occurrence of plunging breaks. The term in a denominator represents relative bar height. A smaller magnitude of the term means a large bar height or smaller bar crest depths, indicating a better lee effect so that the berm is more likely to be accurate when there is no submerged artificial sandbar as often in the equals natural slope and the h bar equals 0 so that it reduces to the classic surface similarity parameters of batteries. As morphological coupling between the submerged artificial sandbar and the berm is revealed by the relationship between shown in the figure. Based on this relationship, it is noted that B increases with the increasing of A and gradually tends to be stable. The morphological coupling reveals the berm responses controlled by bar morphology. The berm undergoes less erosion with projection of the artificial sandbar, which has a smaller crest depth and steeper seaward slope under erosive wave conditions. When B is larger than 1, the berm is accretive compared with the state before nourishment, indicating there is a morphological hysteresis. A berm responds to erosive impacts, while the morphology of artificial sandbar is remarkable. At that time, bar with a steep seaward slope or smaller crest depths efficiently dissipates the incident wave energy. When the bar morphology has decayed with a mild seaward slope and a large crest depth, the morphological hysteresis is vanished, and the berm starts to be eroded with a small b. This finding may be useful to optimize the design of shoreface nourishment, for example, to preserve sand volume during storm by enhancing the morphological hysteresis. For instance, the ratio between bar crest depth to the bar height should be designed to be small, and the seaward slope should be enlarged. This is in line with previous studies on the wave height transmission coefficients of submerged breakwaters or seas. To summarize briefly what we have looked at, the main conclusions are drawn below. Thank you for your listening. Questions are welcome. Thank you.